How can a universe only a few 100 million years old already host a galaxy that looks this grown up, this bright, and this busy, when our best models say it should barely exist at all? That galaxy is called Mom Z14, and right now it holds the record for the most distant confirmed galaxy we've ever seen, using the James Webb Space Telescope. Its light has a redshift of about 14.44. In plain language, that number tells you how much the universe expanded while that light was on the way to us. For Mom Z14, the answer is a lot. That signal left the galaxy only about 280 million years after the Big Bang, when the universe was around 2% of its current age of 13.8 billion years. But before we continue, please subscribe to the channel to give your support. Let's continue. When you hear 13.5 billion years of travel time, that's what astronomers call the look-back time. You're seeing Mom Z14 as it was 13.5 billion years ago, not as it is now. During that entire journey, space itself kept stretching. If you could pause the expansion today and somehow measure the actual separation, Mom Z14 would sit at a proper distance of roughly 34 billion light-years. That sounds impossible because light-years already feel huge. 1 light-year is about 9.5 trillion kilometers, or about 5.9 trillion miles. Now multiply that by 34 billion. You get a distance that is so large it's easier to just say, this is out near the edge of the observable universe, and move on. So you've got a galaxy very close in time to the beginning, extremely far away in distance, and bright enough that JWST can pull it out of the background. That alone would make it special. But if the story stopped there, this would just be a clean record update. Previous record holder, Jade's Z14, was already shocking at a similar redshift. Mom Z14 just pushes that same frontier a little closer to the Big Bang and confirms that these early overachievers are real, not flukes. You might say, all right, it's far away and very early, that's impressive, but maybe it's just a normal small galaxy that happens to be bright. The problem is, it's not normal in any simple way, starting with its size. Mom Z14 is tiny. Current estimates put its size at a few hundred light-years across, roughly 240 light-years if you want a single number. That's the diameter of the main star-forming region. For comparison, the Milky Way is about 100,000 light-years wide. Even some individual star-forming complexes inside our galaxy are larger than Mom Z14's whole visible body. If you turned the Milky Way into a big continent, Mom Z14 would be a single town. Yet that small town is giving off as much ultraviolet light as dwarf galaxies that are thousands of light-years across. So that compact scale matters. In standard galaxy formation pictures, brightness usually comes from having a lot of stars spread out over a much larger region. You can also get bright spots from very intense star clusters, but they are smaller and usually not this dominant at such an early time. Here, you have a system just a couple of hundred light-years wide, at a time when the universe is still cooling down and organizing itself, and it's already acting like a fully fired-up star factory. If you tried to pack this much star formation into a patch of the Milky Way the same size, it would outshine most of our galaxy's disk in the ultraviolet. So, okay, maybe this is just a super efficient little starburst. Small, dense, bright, fine. That would already be a challenge for simulations, but still within the extreme case category. The real trouble starts when you look at what the gas and stars in Mom Z14 are actually made of. When astronomers disperse its light with JWST spectrograph, they don't see the signature of a completely pristine object made of almost pure hydrogen and helium. Instead, they see evidence for heavier elements, the stuff astronomers lump together under the word metals. Things like carbon, oxygen, and in this case, notably, nitrogen. These metals are not left over from the Big Bang. They're made inside stars through nuclear fusion and then injected into the surrounding gas when those stars die, especially in the late stages of certain stars' lives. Nitrogen is particularly interesting. It often comes from stars that are not the most massive, the ones that live a few tens to a few 100 million years before shedding their outer layers. Seeing enhanced nitrogen in Mom Z14 only 280 million years after the Big Bang means that at least one full generation of stars has already formed, evolved, and polluted the gas, and then a second generation has formed out of that enriched material. That means you don't just need fast star formation, you need multiple cycles in a very tight schedule. It's like being told a city was founded last year, but when you visit, you see old apartment blocks being demolished, new buildings going up on top of rubble, and complex plumbing already in place. The timeline feels off. This is why people are talking about Mom Z14 as chemically too mature for its age. The chemical enrichment clock says, I've had time to run several rounds of star formation and death. The cosmological clock says, the universe just started. The two clocks aren't lining up cleanly. At this point, you might ask, isn't it possible that we're just misreading the data? That Mom Z14 is actually closer and older and we've tagged it with the wrong distance? That used to happen with early most distant galaxy candidates, where brown dwarfs or dusty nearby galaxies fooled our instruments. JWST, though, has both deep imaging and high-quality spectroscopy. For Mom Z14, NIRCam images pick it out as a very red source that disappears in the bluer filters, which is exactly what you expect from extreme redshift. Then near-spec spectra show a clear break where hydrogen absorbs light at short wavelengths, shifted deep into the infrared, plus several emission lines at the right positions. Together, those features lock in the redshift at about 14.44 with high confidence. On top of that, the pattern we see in Mom Z14 is consistent with what we see in JADE's GS Z14 and other bright early galaxies. So the odds that this is some weird nearby object are extremely low. The safer conclusion is that the galaxy really is where the data say it is, and really is as bright and as chemically enriched as the models say. That means the discomfort is not in the measurement, it's in our expectations. And this is why cosmologists are uneasy. In the standard Lambda cold dark matter model, which is the framework that fits the cosmic microwave background, galaxy clustering, and a lot of other data, structure grows from small to large over time. Early on, you expect many small, faint, metal-poor galaxies slowly building up inside dark matter halos that are just getting started. You do not expect a crowd of very bright, compact, metal-enriched systems at redshift 14. Before JWST, most simulations and analytic models predicted that these kinds of objects should be extremely rare, at the very edge of what you might see in a deep survey, if at all. But JWST keeps finding them. JADE's GS Z14-0 was already a problem. Mom Z14 is even more extreme. And it's not just one or two galaxies, it's a growing population of too bright, too soon objects at redshift 10 and beyond. Each one of them requires very rapid buildup of dark matter halos, very efficient conversion of gas into stars, and very fast chemical enrichment. Taken together, they start to push hard on the parameters we thought were safe. So here's the core hook for the rest of this story. You're looking at a galaxy only about 240 light-years across, whose light has been on the road for 13.5 billion years, sitting in a universe that's just 2% of its current age, and that galaxy already looks busy, dense, and chemically processed. Either normal matter in the early universe is much better at collapsing, forming stars, and enriching itself than our simulations assumed, or there is something deeper going on with dark matter, dark energy, or even gravity that we haven't fully captured yet. To figure out which of those possibilities is closer to the truth, you need to know how we even managed to detect Mom Z14 in the first place, how a telescope can pick out a tiny red dot at redshift 14 from all the other faint smudges in the sky and be confident it really is that far away. So next, let's talk about the machine that made this possible, and ask a simple question with a very technical answer. What does it actually take to see a galaxy at redshift 14? How do you actually see a galaxy whose light left when the universe was only a couple 100 million years old, and that light has been stretched more than 15 times longer on the way to you? First, the hardware. You are not using a regular telescope in low Earth orbit. The NASA, Canadian Space Agency, and partners parked the James Webb Space Telescope about 1.5 million kilometers from Earth at a point called Sun-Earth L2. That's roughly a million miles away, about 4 times farther than the moon. Out there, JWST can stay cold, stable, and pointed at the same patch of sky for days or weeks. Its primary mirror is 6.5 meters across, about 21 feet, built from 18 gold-coated hexagonal segments. That collecting area is around 6 times larger than the main mirror on the Hubble Space Telescope. So for the same exposure time, Webb simply grabs a lot more photons. And unlike Hubble, which is strongest in visible and ultraviolet light, JWST's 4 science instruments are tuned for the infrared, exactly where the ancient, stretched-out light from galaxies like Mom Z14 shows up. So the basic idea is you put a huge, very cold, infrared-optimized eye in a quiet orbit, far from Earth's heat and glow, and let it stare for a long time. That gives you the raw sensitivity you need. But sensitivity alone doesn't explain how you know that a tiny red smudge is really sitting at redshift 14.44 and not just at, say, redshift 5 or 6. That's where the stretching of the universe becomes the main tool. Redshift is just a measure of how much the wavelength of light has been stretched by cosmic expansion. For Mom Z14, the redshift is about 14.44. That means the universe has expanded by a factor of a bit more than 15 between the moment those photons left the galaxy and the moment they hit JWST. In practical terms, take a photon from hydrogen's Lyman alpha transition, which originally sits in the ultraviolet at about 121.6 nanometers. By the time it reaches Webb from Mom Z14, that same feature has slid out to almost 1.9 micrometers, deep in the infrared band. That is why you need an infrared telescope for this job. Visible light telescopes are basically blind to this signal because the light has been shifted out of their range by the expansion of space itself. The nice thing about this stretching is that it's not random. For a given redshift, every spectral feature shifts by the same factor. So if you can spot a sharp cutoff or a known emission line at a new wavelength, you can back out the expansion factor and therefore the redshift. That's the foundation of the whole distance measurement here. But before you ever get a spectrum, you have to find the candidate galaxy in the first place, and that's where JWST's NIRCam comes in. Think of NIRCam as Webb's deep field camera. It takes very long exposures through multiple filters that each admit a specific slice of infrared wavelengths. High redshift galaxies show a very particular pattern in those filters because of something called the Lyman break. Neutral hydrogen in and around a galaxy strongly absorbs light shorter than a certain ultraviolet wavelength. Once that break gets redshifted into the infrared, it causes the galaxy to basically disappear in filters that cover shorter wavelengths, while it remains visible in redder filters. This is called the dropout technique. You look for objects that drop out of the bluer filters but pop up in the redder ones. For Mom Z14, the NIRCam images show exactly that behavior. In filters sensitive to wavelengths shorter than about 1.8 micrometers, you see nothing at that position, just background noise. Then, suddenly, in the reddest filters, a compact source appears. That color pattern by itself already screams very high redshift. This is the same strategy that flagged earlier record holders like Jade's GS Z14-0, an object that is invisible in all the bluer JWST filters and only shows up in the longest wavelength ones, is a classic extreme redshift candidate. But color alone is not enough. Before JWST, many most distant galaxy announcements came from photometric redshifts like this, and later turned out to be wrong. Brown dwarfs in our own galaxy or dusty, moderate redshift galaxies can sometimes mimic the same color pattern. So once NIRCam has built the shortlist, you need a second instrument to go in and turn that smeared out light into something you can measure precisely. That's the job of NIRSpec. NIRSpec is Webb's near-infrared spectrograph. Instead of taking a picture, it spreads the incoming light from a target out into a spectrum, basically brightness as a function of wavelength. For Mom Z14, NIRSpec observes a clear, sharp break in the spectrum, where the flux drops off at shorter wavelengths because of hydrogen absorption and then picks up again at longer wavelengths. On top of that, it detects several faint emission lines at specific wavelengths in the rest frame ultraviolet that have been shifted into the near-infrared. By matching those features to known transitions of elements like hydrogen and nitrogen and measuring exactly where they land in wavelength, astronomers can determine the redshift with very small uncertainty, way better than 1%. For Mom Z14, that process gives you about 14.44 plus or minus a few hundredths. That level of precision is impressive when you remember what we're talking about. On the sky, Mom Z14 is just a faint, barely resolved dot. You're collecting a tiny trickle of photons from a galaxy only about 240 light-years across from more than 13 billion years of lookback distance, with all the usual background noise, detector effects, and cosmic rays on top. Yet the combination of long integration times, a huge mirror, and modern infrared detectors is enough to pull out not just there is a galaxy here, but this is its distance, within tens of millions of years in cosmic time. So how should you trust that this isn't another misidentification like earlier eras when high redshift claims later collapsed? Two things make the new generation of detections, including Mom Z14 and JWST Z14-0, much harder to fake. First, you have deep multi-filter imaging from NIRCam that gives a very clean dropout pattern with good signal-to-noise. Second, you have spectroscopic confirmation from NIRSpec that directly shows the Lyman break and multiple emission lines at consistent redshift. In the case of JWST Z14-0, there is even a third independent check from the Atacama Large Millimeter and Submillimeter Array, which detects an oxygen emission line in the millimeter band at exactly the wavelength you expect for a redshift of about 14.2. When space-based infrared spectroscopy and ground-based millimeter spectroscopy agree, the distance is basically locked in. For Mom Z14 specifically, NASA has released NIRCam images and confirmed that NIRSpec sees the same kind of sharp hydrogen break and rest ultraviolet emission lines, giving that redshift around 14.44. Independent groups have reanalyzed the data and get consistent answers. At this point, the scenario where Mom Z14 is actually some weird nearby object pretending to be a galaxy at cosmic dawn is extremely unlikely. The simplest explanation is that it really is what the data say: a compact, very bright, chemically active galaxy seen just 280 million years after the Big Bang. So, step back and summarize what it takes to see it. You place a 6.5 meter infrared telescope 1.5 million kilometers from Earth, keep it cold, stare at one patch of sky long enough to build up ultra-deep images, use color dropouts to flag extreme redshift candidates, then use a sensitive spectrograph to measure the stretched-out fingerprints of hydrogen and other elements and turn that into a precise redshift. That pipeline is how Mom Z14 goes from an invisible nothing, invisible light to a hard data point at the edge of the observable universe. Now that you know how we're even able to see this thing, the next question is where exactly it sits on the universe's timeline. How early 280 million years after the Big Bang really is compared to everything else you know, and why that timing makes Mom Z14 such a serious headache for our models. How early is too early for a galaxy like Mom Z14 to exist? And where does it actually sit on the full history of the universe? Not just as a big, scary number on a slide, but on a timeline you can picture. Start with the basic scale. The best current measurements say the universe is about 13.8 billion years old. The light from Mom Z14 left when the universe was roughly 280 million years old. So you're not looking halfway back. You're looking back to about the first 2% of cosmic time. Think of the entire history of the universe compressed into one normal year, 365 days. In that cosmic year, the Big Bang hits at midnight, January 1st. On that same scale, Mom Z14 lights up in the first week of January, around day 7. The Milky Way's main disk doesn't really settle in until late March. The Sun and Earth show up in early September. Dinosaurs walk in December. Modern humans arrive at about 11:52 p.m. on December 31st, in the last few minutes of the last day. Mom Z14 is way back at the beginning of the calendar, when the universe is still setting up basic structure, yet it already looks busy and chemically evolved. So, what was the universe actually like between midnight on January 1st and day 7, when Mom Z14 is shining? Right after the Big Bang, the universe was a hot, dense plasma of particles and radiation. As it expanded and cooled, protons and electrons finally combined to form neutral hydrogen and helium. That happened about 380,000 years after the Big Bang, when the universe went from opaque to transparent and the cosmic microwave background was released. After that, there were no stars yet, no galaxies, just a huge, mostly uniform sea of neutral gas slowly responding to gravity. Astronomers call the stretch between that moment and the birth of the first stars the cosmic dark ages, because there was no starlight in visible or ultraviolet wavelengths, only the leftover microwave glow. Mom Z14 sits right after that dark phase, in the period called cosmic dawn. This is when the first stars and galaxies switch on, inside the first dark matter halos that grew from tiny density fluctuations. Those first stars are expected to be very hot and very bright in ultraviolet light, and they start to light up and heat the neutral hydrogen gas around them. Mom Z14 is part of that wave of early activity. By redshift 14 or so, the universe has gone from a smooth gas background to a lumpy structure with dark matter halos, gas flows, and active star-forming systems punching through the darkness. The fact that Mom Z14 is not just forming its first stars, but already shows enriched gas and intense star formation means it's not at the very spark, but still deep in that dawn period where structure is just getting going. Now, there's another key process happening in this era: reionization. After the universe became neutral, most hydrogen atoms were holding on to their electrons. When the first generations of stars and later black holes started producing large numbers of high-energy ultraviolet photons, those photons began knocking electrons off hydrogen again, turning the gas back into an ionized plasma, but this time very diffuse and transparent. That transition from mostly neutral to mostly ionized hydrogen across intergalactic space is called cosmic reionization. Observations of distant quasars and the cosmic microwave background suggest that reionization was mostly finished by redshift 6, which corresponds to roughly 1 billion years after the Big Bang. At that point, the intergalactic medium is largely ionized. Mom Z14 is operating much earlier than that, when reionization has barely started. You can think of the universe at that time as a neutral fog with growing ionized bubbles around early galaxies. Mom Z14 would be one of the strong sources carving out a local ionized region around itself. Its stars are sending out a huge number of ultraviolet photons, and some fraction of those escape into space and help eat away at the neutral hydrogen. So, on the reionization timeline, Mom Z14 is not at the end of the process, cleaning up the last neutral pockets. It's closer to the start, when the first serious holes are being punched through the fog. Now, let's pin down the distance side again, because far can mean different things. When you hear 13.5 billion light-years away in videos or articles, that's usually the look-back time translated into distance units. The time the light has been in flight times the speed of light. It's a useful number, but it's not the same as the present-day separation. Because the universe expanded while that light was traveling, the actual proper distance to Mom Z14 today is around 34 billion light-years. That's the distance you'd get if you could freeze the expansion right now and lay down a very, very long ruler. To make that a bit more concrete without going overboard, take a typical long-haul jet. Say it flies at about 900 kilometers per hour, roughly 560 miles per hour. If you tried to cover 34 billion light years at that speed, you'd need on the order of 40 trillion years of flight time. That's around 3,000 times the current age of the universe. So in practical terms, everything about this system is operating on scales completely beyond normal human travel, or even normal astrophysical distances inside a galaxy. It's at the edge of what we can see, both in time and in space. All of that sets up the real problem, which is timing. There's a clock built into gravity and gas physics. To go from a mostly uniform hydrogen-helium mix to a compact galaxy like Mom Z14 with hundreds of millions of solar masses of stars, you need several steps. First, dark matter has to clump into a halo big enough to pull in gas. Then that gas has to cool and sink into the center of the halo. Once it's dense enough, it fragments into clouds that collapse into stars. Those stars live their lives, some of them explode, they enrich the gas with heavier elements, and that enriched gas forms new stars. Each stage has physical limits on how fast it can happen. Cooling takes time. Cloud collapse takes time. Stellar evolution, especially for the kinds of stars that make elements like nitrogen, takes tens to hundreds of millions of years. When you look at Mom Z14 at 280 million years after the Big Bang, and you see strong star formation plus clear signs of chemical enrichment, you are forced to squeeze all of those stages into that short window. For Mom Z14 to have its inferred stellar mass, you're talking about average star formation rates of several to a few tens of solar masses per year, sometimes in bursts where the rate is even higher. In metric terms, that's roughly converting on the order of 10 to the 31 kilograms of gas into new stars every year. In Earth terms, that's roughly a few Earth masses of gas being turned into new stars, sustained over a significant chunk of that 280 million year window. On top of that, you need enough massive stars to enrich the gas quickly, and enough intermediate mass stars to start pumping out elements like nitrogen. You need feedback from supernovae and stellar winds that is strong enough to mix metals into the gas, but somehow not so strong that it completely shuts down star formation in this tiny 240 light-year region. And you have to fit all of this into a time slot that, on the cosmic calendar, is just the first week of January. That's what makes the timing so tight. It's not that star formation at that rate is impossible in principle. We see intense starbursts in the local universe. It's that doing it this early, this compact, with this level of chemical maturity pushes the standard models hard. So when cosmologists say Mom Z14 is too early or too fast, they're really talking about that chain of physical steps. The distance, the age of the universe, the reionization stage, all line up to tell you that by 280 million years in, this galaxy has already raced through several phases that our simulations usually spread out over longer periods. That's why Mom Z14 isn't just a cool dot on a JWST image. It's a timing test. And right now, it's a test our standard galaxy formation recipes are struggling to pass without turning a lot of knobs to extreme settings. Which leads directly to the next tension-raising question. If Mom Z14 isn't just early, but also beating expectations on size, density, and chemistry, how does it compare to the previous record holder, JADE's GS-Z14-0? And what happens when you put those two galaxies side by side and realize this is a pattern, not a one-off? How bad is it when the galaxy that used to be your "this should not exist" problem suddenly becomes the more normal one because an even more extreme object just showed up right next to it in time? Before Mom Z14, the big headache was JADE's GS-Z14-0. That galaxy came out of some of the deepest JWST observations in the JADES field, using NIRCam to find faint red sources and NIRSpec to lock in their distances. Its spectroscopic redshift is about 14.2 to 14.3, which means you're seeing it less than 300 million years after the Big Bang, again at around 2% of the universe's current age. For a while, that was the distance record, and it already looked uncomfortably bright and active for such an early time. So what happens when you put JADE's GS-Z14-0 next to Mom Z14 and actually compare them in detail, not just as record holders, but as physical objects? Start with size and brightness, because that's where the contrast jumps out. JADE's GS-Z14-0 is estimated to be roughly 1,500 to 1,600 light-years across. Mom Z14, in contrast, comes in at about 240 light-years in diameter. So JADE's GS-Z14-0 is around 7 times larger in linear size. Yet both galaxies are extremely bright in the rest frame ultraviolet. They're each putting out enough UV light to land in the luminous bin of early galaxies, the ones that stand out in deep JWST surveys. Mom Z14 is narrower, more compact, but its luminosity is in the same ballpark as a system several times larger. It's like taking the same total lighting and squeezing it into a much smaller room. The energy output per cubic light year in Mom Z14 is just on another level. That alone is a problem for formation models, because getting that kind of brightness requires either a very high star formation rate, a very efficient conversion of gas into massive stars, or both. Doing that across 1,600 light-years in JADE's GS-Z14-0 is tough, but maybe just manageable in extreme scenarios. Doing it inside 240 light-years in Mom Z14 pushes densities, feedback, and stability in a much more extreme direction. If you run simulations with standard assumptions about star formation and feedback, it's easier to light up a puffed-up, clumpy system like JADE's GS-Z14-0 than a hyper-compact one like Mom Z14. The fact that the compact one is at slightly earlier cosmic time makes it even more uncomfortable. But the comparison is not only about size and UV brightness, it's also about chemistry. And this is where JADE's GS-Z14-0 started the alarm that Mom Z14 is now amplifying. Follow-up observations of JADE's GS-Z14-0 with the ALMA array detected an oxygen emission line at 88 micrometers in the galaxy's rest frame. By the time that line reaches us, it's been stretched into the millimeter range. That detection gives a very precise redshift of about 14.18, but more importantly, it tells you that this galaxy already contains a significant amount of oxygen. Oxygen is produced in the cores of massive stars and is released into the interstellar medium when those stars explode as core collapse supernovae. So if you see strong O3 88 micrometer emission at redshift 14, that means at least one earlier generation of massive stars has had time to form, live a few million years, explode, and enrich the gas. That level of chemical maturity at such an early time was already pushing the models. Standard simulations expected galaxies at redshift 14 to be mostly metal poor, with very weak metal element lines, because there simply shouldn't have been enough time to run a lot of star formation cycles. JADE's GS-Z14-0 broke that expectation by showing clear oxygen. Mom Z14 comes in and adds another enriched system at almost the same epoch, but with that extra twist of being more compact and showing strong nitrogen features as well. Together, they say chemical enrichment in some regions of the early universe was much faster and more efficient than we thought. So maybe you think, okay, we've got two overachievers. Maybe this patch of the sky is just a rare, lucky overdensity. Maybe we got unlucky in a statistical fence and pointed at a freak region. That would be the comforting story. Yes, they're extreme, but they're just rare outliers sitting in a special environment. The issue is that JWST deep fields across different parts of the sky are finding a similar trend. When astronomers measure the ultraviolet luminosity function, basically how many galaxies you get at each brightness at high redshift, they're finding that bright galaxies at redshift above 10 and even into the 12 to 15 range are more common by roughly a factor of 10 compared to pre-JWST extrapolations. For every bright early galaxy models said you might see, JWST is seeing many more. JADE's GS-Z14-0 was the first clear marker at the extreme bright end. It said there is at least one very luminous, chemically mature galaxy at redshift 14. Mom Z14 is a follow-up that says, and there is another, slightly earlier, even more compact with its own set of extreme properties. Combine those with the growing census of bright galaxies at redshift 10 through 13, and the picture looks less like a couple of freaks and more like the high redshift universe being systematically more active, at least in some halos, than our models allowed. That's why papers keep talking about a tension with a UV luminosity function, and why people are now reworking both galaxy formation physics and, in some cases, cosmological assumptions to try to fit these numbers. Now, what makes Mom Z14 stand out even more, beyond just beating the distance record, is what its structure and chemistry might be telling you about what is forming there. Because it's so compact, on the order of a few hundred light years, and because its spectra suggest high nitrogen enrichment relative to what you'd expect at that time, some researchers have started to draw a parallel to massive star clusters or proto-globular clusters in the local universe. Globular clusters around the Milky Way today are dense, roughly spherical groups of old stars, typically 10 to 30 light-years across, with characteristic chemical patterns, including unusual nitrogen and other element ratios. Mom Z14 looks in some ways like a scaled-up, younger ancestor of that kind of object. It's much larger than a present-day globular cluster, but still tiny for a whole galaxy, and it's already showing complex chemistry early on. One idea is that what we're seeing in Mom Z14 is not a finished galaxy in the sense of the Milky Way, but a very early, intense phase of cluster-like star formation that could later evolve into one or more dense stellar systems, possibly the seeds of globular clusters. If that's right, you're not just seeing an early galaxy, you're watching the very first building blocks of the dense clusters that now orbit big galaxies like ours. That possibility matters because globular clusters have always been a bit of a puzzle. They are old, they are dense, and they show chemical patterns that suggest complicated star formation histories in the first billion years of cosmic time. If Mom Z14 is an example of the kind of environment where those clusters are born, then JWST is giving you direct access to the missing chapter of their origin story. At the same time, it's ramping up the pressure on simulations, because now models have to explain not only why there are more bright galaxies early on, but also how such compact, chemically processed, cluster-like objects can appear so fast. So the tension rises in two ways when you compare Mom Z14 and JADE's GS-C14-0. First, they show that bright, metal-enriched galaxies at redshift 14 are not unique. Second, Mom Z14 in particular pushes you towards interpreting at least some of these early objects as extremely dense star cluster factories, not just scaled-down versions of normal galaxies. Either way, you're being told that the early universe was better at rapidly organizing matter into intense, high-density star-forming regions than you thought. And that leads straight into the next hard question. If you zoom in on Mom Z14 itself, what kind of star formation rates, stellar densities, and dark matter halos are you actually talking about? And do those numbers fit anywhere inside the usual lambda cold dark matter story without breaking something else? How extreme does a galaxy have to be before you start wondering if the physics you've been using in your simulations is missing whole pieces, not just a few tuning parameters? For Mom Z14, the numbers you get when you actually run through the basic estimates are not just big, they're stacked in a way that makes almost everything about it feel pushed to the limit. Start with the stellar mass. From its brightness in the rest frame ultraviolet and how its light is distributed across different infrared filters, astronomers build what's called a spectral energy distribution. Basically a curve of how bright it is at each wavelength. Then they compare that to models of stellar populations at different ages and metallicities. When they do that for Mom Z14, they get stellar masses in the range of a few times 10 to the 8th solar masses, so a few 100 million suns worth of stars, maybe pushing toward 10 to the 9th solar masses, depending on the exact assumptions about the stellar population. That's starting to get into the ballpark of the Small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way today. Now, the size. Mom Z14 is not spreading those hundreds of millions of stars over tens of thousands of light years. The main star-forming region is only about 0.05 to zero point 0.1 kiloparsecs across, which is roughly 150 to 300 light years. So you're taking a mass similar to a decent-sized dwarf galaxy and squeezing it into a volume only a few hundred light years wide. That gives you a stellar density that is far above what you see in the disk of the Milky Way, and even comparable to or higher than what you see in the cores of dense star clusters. It's like taking all the stars in a dwarf galaxy and packing them into a cube a few hundred light years on a side. At that point, gravity, gas pressure, radiation, and feedback are all operating in a very intense, very crowded environment. From that mass and brightness, you can back out a star formation rate. The ultraviolet light you see is mostly coming from short-lived, massive, hot stars. They don't live long, so a high UV luminosity usually means a high current rate of forming new stars. For Mom Z14, estimates put the star formation rate at several to maybe a few tens of solar masses per year. Let's pick a middle value and say around 10 solar masses per year just to have a number in your head. One sun is about 2 times 10 to the 30th kilograms, so 10 solar masses per year is about 2 times 10 to the 31st kilograms of gas being turned into stars every year. If you translate that into something more intuitive, Earth has a mass of about 6 times 10 to the 24th kilograms, so 2 times 10 to the 31st kilograms per year is roughly 3 Earth masses per second being converted into stars, continuously, in a region only a few hundred light years across. That is what starburst mode means here. This is not a calm, slowly growing galaxy. This is a compact machine slamming gas into stars at a rate that would qualify as an intense starburst even in the nearby universe. And remember, it's doing this when the universe itself is only 280 million years old. Now, think about what that environment must actually be like inside. When you form a lot of massive stars in a small volume, you don't just get light. You get stellar winds, streams of fast particles blowing out from hot stars. You get strong radiation pressure, where photons themselves push on gas and dust. And very quickly, you start getting supernova explosions as the most massive stars reach the ends of their short lives, dumping energy and heavy elements into the gas. All of that is what astronomers group under feedback. Feedback is a big deal in galaxy formation models because it can both trigger and shut down star formation. Winds and explosions can compress nearby gas, causing new stars to form, but they can also blow gas out of the galaxy, heat it up, and make it harder for it to cool and collapse. In many simulations, especially for small galaxies at early times, feedback is so strong that it basically chokes off star formation after a short burst. The system lights up, blows out a lot of its gas, and then has to wait for new gas to fall in before it can restart. In Mom Z14, you clearly have massive feedback happening. With that many hot stars in a compact region, the local interstellar medium must be full of shock waves, hot bubbles, and outflows. Yet the galaxy is still extremely bright in UV, meaning star formation is still going hard, or has recently ramped back up. So either the feedback is somehow less efficient at shutting things down than in our models, or the gas supply is so strong and so continuous that even heavy feedback can't stop the overall burst for long. You end up with a picture of a small galaxy that is more like a sustained war zone. Gas coming in, stars forming, explosions going off, and the whole cycle repeating on short timescales. That brings you straight to the question of fuel. You don't get star formation rates of several to tens of solar masses per year without a serious flow of fresh gas. In the standard Lambda cold matter framework, galaxies live inside dark matter halos. Those halos pull in gas from the cosmic web along filaments. For a galaxy as bright as Mom Z14 at such an early time, typical models suggest it should sit in a dark matter halo with a mass in the range of 1 billion to 10 billion solar masses, maybe more. That's 1 billion to 10 billion times the mass of the sun in dark matter, plus the gas it pulls in. The tension is not that such halos can never exist at redshift 0.14, but that they're supposed to be very rare. The standard halo mass function, the predicted number of halos of each mass at each time, drops off steeply at the high end mass, especially at early times. To have a galaxy like Mom Z14, you need a relatively massive halo to have formed very early, accumulated gas quickly, and then converted that gas into stars with unusually high efficiency. If you only had one such object across the entire sky, you could maybe call it an extreme tail event. But JWST is now seeing enough bright early galaxies that it starts to push on that halo mass function. Are there more massive halos at early times than ЛCDM predicts? Or are the halos the same, but the gas physics much more efficient than we assumed? That's one of the core questions Mom Z14 throws at the theory side. Finally, loop back to the idea that Mom Z14 might not just be a small galaxy, but a laboratory for star cluster physics in the early universe. Because it's so compact and dense, and because its chemical fingerprints look complex already, it's a natural place to study conditions that could lead to the formation of very massive clusters of stars. Today's globular clusters in the Milky Way are typically 10 to 30 light-years across, packed with hundreds of thousands to millions of stars, and they show chemical patterns that suggest multiple generations of star formation in a dense environment early on. Mom Z14, at a few hundred light-years across with hundreds of millions of solar masses of stars, could host several proto-cluster regions inside it. It might be the kind of intense early environment where those future globular clusters are born. That means when you analyze its density, its star formation rate, its feedback, and its halo, you're not just doing a weird edge case problem. You're probing the conditions that might have created some of the most ancient and puzzling stellar systems we see around us today. So at this point, you have a compact galaxy only a few hundred light-years wide, with a stellar mass approaching that of a local dwarf galaxy, forming stars at a rate of several to tens of suns per year inside a dark matter halo of at least 1 billion solar masses, all of that being squeezed into the first 280 million years of cosmic time. That naturally leads to the next step in the tension. If Mom Z14 is this dense, this fast, and this chemically mature, what do its heavy elements actually tell you about the clock of star formation in the early universe? And at what point does the metallicity start to look flat out too rich for the age of the cosmos? How grown up is the chemistry in Mom Z14 really? And at what point does metal rich for its time start to look flat out inconsistent with the age of the universe? First, you need to be clear about what astronomers mean by metals, because it's not the everyday meaning. In cosmology and astrophysics, everything heavier than helium gets thrown into the metals bucket. Carbon, oxygen, nitrogen, silicon, iron, all of it counts as metals. The Big Bang itself made almost only hydrogen and helium, plus a tiny bit of lithium. That's it. No carbon, no oxygen, no nitrogen. All the heavier elements had to be cooked later inside stars through nuclear fusion and supernova explosions. So anytime you see metals in a galaxy, you're seeing the fingerprints of earlier generations of stars that have already lived and died. Metals are literally a record of stellar history. For Mom Z14, the numbers you get when you actually run through the basic estimates are not just big, they're stacked in a way that makes almost everything about it feel pushed to the limit. Start with the stellar mass. From its brightness in the rest frame ultraviolet and how its light is distributed across different infrared filters, astronomers build what's called a spectral energy distribution, basically a curve of how bright it is at each wavelength. Then they compare that to models of stellar populations at different ages and metallicities. When they do that for Mom Z14, they get stellar masses in the range of a few times 10 to the 8th solar masses, so a few 100 million suns worth of stars, maybe pushing toward 10 to the 9 solar masses, depending on the exact assumptions about the stellar population. That's starting to get into the ballpark of the Small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way today. Now, the size. Mom Z14 is not spreading those hundreds of millions of stars over tens of thousands of light years. The main star-forming region is only about 0.05 to 0.1 kiloparsecs across, which is roughly 150 to 300 light years. So you're taking a mass similar to a decent-sized dwarf galaxy and squeezing it into a volume only a few hundred light years wide. That gives you a stellar density that is far above what you see in the disk of the Milky Way, and even comparable to or higher than what you see in the cores of dense star clusters. It's like taking all the stars in a dwarf galaxy and packing them into a cube a few hundred light years on a side. At that point, gravity, gas pressure, radiation, and feedback are all operating in a very intense, very crowded environment. From that mass and brightness, you can back out a star formation rate. The ultraviolet light you see is mostly coming from short-lived, massive, hot stars. They don't live long, so a high UV luminosity usually means a high current rate of forming new stars. For Mom Z14, estimates put the star formation rate at several to maybe a few tens of solar masses per year. Let's pick a middle value and say around 10 solar masses per year just to have a number in your head. One sun is about 2 times 10 to the 30 kilograms, so 10 solar masses per year is about 2 times 10 to the 31 kilograms of gas being turned into stars every year. If you translate that into something more intuitive, Earth has a mass of about 6 times 10 to the 24 kilograms, so 2 times 10 to the 31 kilograms per year is roughly 3 Earth masses per second being converted into stars continuously in a region only a few hundred light years across. That is what starburst mode means here. This is not a calm, slowly growing galaxy. This is a compact machine slamming gas into stars at a rate that would qualify as an intense starburst even in the nearby universe. And remember, it's doing this when the universe itself is only 280 million years old. Now, think about what that environment must actually be like inside. When you form a lot of massive stars in a small volume, you don't just get light, you get stellar winds, streams of fast particles blowing out from hot stars. You get strong radiation pressure, where photons themselves push on gas and dust. And very quickly, you start getting supernova explosions as the most massive stars reach the ends of their short lives, dumping energy and heavy elements into the gas. All of that is what astronomers group under feedback. Feedback is a big deal in galaxy formation models because it can both trigger and shut down star formation. Winds and explosions can compress nearby gas, causing new stars to form, but they can also blow gas out of the galaxy, heat it up, and make it harder for it to cool and collapse. In many simulations, especially for small galaxies at early times, feedback is so strong that it basically chokes off star formation after a short burst. The system lights up, blows out a lot of its gas, and then has to wait for new gas to fall in before it can restart. In Mom Z14, you clearly have massive feedback happening. With that many hot stars in a compact region, the local interstellar medium must be full of shock waves, hot bubbles, and outflows. Yet, the galaxy is still extremely bright in UV, meaning star formation is still going hard, or has recently ramped back up. So either the feedback is somehow less efficient at shutting things down than in our models, or the gas supply is so strong and so continuous that even heavy feedback can't stop the overall burst for long. You end up with a picture of a small galaxy that is more like a sustained war zone, gas coming in, stars forming, explosions going off, and the whole cycle repeating on short timescales. That brings you straight to the question of fuel. You don't get star formation rates of several to tens of solar masses per year without a serious flow of fresh gas. In the standard Lambda cold dark matter framework, galaxies live inside dark matter halos. Those halos pull in gas from the cosmic web along filaments. For a galaxy as bright as Mom Z14 at such an early time, typical models suggest it should sit in a dark matter halo of a mass in the range of 10 to the 9 to 10 to the 10 solar masses, maybe more. That's 1 billion to 10 billion times the mass of the sun in dark matter, plus the gas it pulls in. The tension is not that such halos can never exist at redshift about 14, it's that they're supposed to be very rare. The standard halo mass function, the predicted number of halos of each mass at each time, drops off steeply at the high mass end, especially at early times. To have a galaxy like Mom Z14, you need a relatively massive halo to have formed very early, accumulated gas quickly, and then converted that gas into stars with unusually high efficiency. If you only had one such object across the entire sky, you could maybe call it an extreme tail event. But JWST is now seeing enough bright early galaxies that it starts to push on that halo mass function. Are there more massive halos at early times than LDCM predicts? Or are the halos the same, but the gas physics much more efficient than we assumed? That's one of the core questions Mom Z14 throws at the theory side. Finally, loop back to the idea that Mom Z14 might not just be a small galaxy, but a laboratory for star cluster physics in the early universe. Because it's so compact and dense, and because its chemical fingerprints look complex already, it's a natural place to study conditions that could lead to the formation of very massive clusters of stars. Today's globular clusters in the Milky Way are typically 10 to 30 light-years across, packed with hundreds of thousands to millions of stars, and they show chemical patterns that suggest multiple generations of star formation in a dense environment early on. Mom Z14 at a few hundred light-years across with hundreds of millions of solar masses of stars could host several protocluster regions inside it. It might be the kind of intense early environment where those future globular clusters are born. That means when you analyze its density, its star formation rate, its feedback, and its halo, you're not just doing a weird edge case problem, you're probing the conditions that might have created some of the most ancient and puzzling stellar systems we see around us today. So, at this point, you have a compact galaxy only a few hundred light-years wide, with a stellar mass approaching that of a local dwarf galaxy, forming stars at a rate of several to tens of suns per year, inside a dark matter halo of at least 1 billion solar masses, surrounded by violent feedback, and still managing to keep the starburst going. All of that is being squeezed into the first 280 million years of cosmic time. That naturally leads to the next step in the tension. If Mom Z14 is this dense, this fast, and this chemically mature, what do its heavy elements actually tell you about the clock of star formation in the early universe? And at what point does the metallicity start to look flat out inconsistent with the age of the cosmos? How grown up is the chemistry in Mom Z14? And at what point does metal rich for its time start to look flat out inconsistent with the age of the universe? First, you need to be clear about what astronomers mean by metals, because it's not the everyday meaning. In cosmology and astrophysics, everything heavier than helium gets thrown into the metals bucket. Carbon, oxygen, nitrogen, silicon, iron, all of it counts as metals. The Big Bang itself made almost only hydrogen and helium, plus a tiny bit of lithium. That's it. No carbon, no oxygen, no nitrogen. All the heavier elements had to be cooked later inside stars, through nuclear fusion and supernova explosions. So anytime you see metals in a galaxy, you're seeing the fingerprints of earlier generations of stars that have already lived and died. Metals are literally a record of stellar history. Now, look at Mom Z14 with that in mind. When JWST splits its light and you fit models to the spectrum, you don't get a picture of a completely pristine first-generation system made out of untouched Big Bang gas. Instead, the best-fitting models show clear signs of heavy elements, and in particular, they suggest enhanced nitrogen compared to what you'd expect for a truly primordial galaxy. That matters because nitrogen often traces stars that are not the most massive, but not tiny either, intermediate mass stars. These stars live on timescales of tens to hundreds of millions of years before they start shedding their outer layers and releasing nitrogen into the surrounding gas. So if Mom Z14 is sitting only about 280 million years after the Big Bang, and you already see a noticeable nitrogen signal, that tells you something very specific. It means at least one full generation of stars has formed out of hydrogen-helium gas, lived long enough for some of the intermediate mass ones to process material and eject nitrogen. And then, a new generation of stars has formed out of that enriched gas. In other words, you're not just seeing a first wave of star formation. You're seeing a second wave that already carries the chemical memory of the first. All of that has to fit into that 280 million year window. Then, put that next to Jade's GS-Z14-0, Mom Z14's slightly older cousin at a redshift of about 14.2. ALMA picks up a strong O3 emission line at 88 micrometers in the rest frame of that galaxy, which is only possible if there's already a decent amount of oxygen in its gas. Oxygen, unlike nitrogen, mostly comes from the most massive stars. Those big stars live fast and die young, a few million to maybe a couple of tens of millions of years before they go supernova. That means you can, in principle, generate oxygen fairly quickly after the first burst of star formation. But to get an oxygen signal strong enough for ALMA to see at a distance like that, you need a lot of massive stars, spread across the galaxy, exploding and enriching the interstellar medium. That implies a very intense, rapid phase of star formation very early on. So in both galaxies, there's a pattern. Jade's GS-Z14-0 is shouting, "We've already made a lot of oxygen," and Mom Z14 is hinting, "We've already made a lot of nitrogen." Together, they say the early universe didn't just flip on the first lights, it cranked straight into heavy chemical processing. You can put some rough numbers on this with metallicity, which is just a fraction of a galaxy's mass that is in metals rather than hydrogen and helium. When people model these early galaxies, they often get metallicities around 10 to 20% of the sun's metallicity, so maybe 1/10 to 1/5 as metal-rich as the gas around the sun today. At first glance, that might sound low. Only 10% of solar, what's the big deal? But remember where these objects sit in time. At redshift 14, we're in the first few hundred million years of the universe. Standard models before JWST usually predicted metallicities closer to 1% of solar, or even lower at these epochs, especially for typical galaxies, not just the brightest ones. So getting up to 10 to 20% solar metallicity by 280 to 300 million years is like looking at a 6-year-old child and realizing they already have a university degree. It's not impossible in an absolute sense if you push everything to the extreme, but it's way ahead of the schedule you expected. To hit those numbers, you need rapid, repeated star formation, efficient mixing of metals into the gas, and not too much gas being blown out of the system by feedback. The underlying reason all of this is troubling is chemical enrichment isn't just a random detail, it's a clock. Every time a generation of stars forms, lives, and dies, it adds to the metal content of the galaxy. More metals usually mean more time has passed and more stellar generations have cycled through. When you see relatively high metallicity, strong oxygen lines, and enhanced nitrogen in galaxies this early, that chemical clock is telling you, I have already gone through several rounds of star formation. But the universe's own age clock at that redshift is saying, you've only had a couple of 100 million years to work with. You can reconcile that in two main ways. One option is to say the early universe was simply more extreme than we assumed. Maybe the first stars formed with a top-heavy distribution, with many more massive stars per unit mass than we see today, so they produced metals faster. Maybe star formation efficiency in dense, early halos was much higher, so gas turned into stars more quickly and mixing was more effective. In that case, you keep the basic lambda cold dark matter framework, but you admit that your recipes for star formation, feedback, and mixing were too conservative. The other option, if these metal-rich, ultra-early galaxies keep showing up in larger numbers with similar or even higher metallicities, is more radical. At some point, if you cannot make the chemical clock and the age clock line up with any reasonable star formation physics, you're forced to look at whether your assumptions about initial conditions, dark matter behavior, or gravitational growth rates at very early times are incomplete. You don't throw out the whole cosmological model based on a handful of data points, but you do have to take seriously the possibility that some part of the early structure formation picture is missing or miscalibrated. Right now, most people in the field are still trying hard to solve this on the astrophysics side. More aggressive star formation histories, different initial mass functions, more complex feedback and mixing, because that's the less drastic move. But Mom Z14, with its strong hints of rapid nitrogen enrichment, and Jade's GS-Z14-0 with its clear oxygen signal, are both pushing that approach close to its limits. If future JWST and ALMA observations find even higher metallicities at similar or even earlier times, the pressure will only increase. And that brings you to the next level of the problem. Even if you accept extreme star formation and very fast enrichment, there's still the question of how many of these galaxies exist, how bright they are, and how massive their dark matter halos have to be. At what point do the counts, the masses, and the halo statistics collectively stop fitting inside the standard lambda cold dark matter box? Why is a small, bright, metal-rich galaxy at redshift 14 such a big deal for theory, when on paper, we already have a model of the universe that explains almost everything else we throw at it? The starting point is the framework everyone in cosmology still uses as the default, lambda cold dark matter, usually written as LCDM. Inside that overall framework, there's a clear story for how structure is supposed to grow. It's hierarchical, or bottom-up. Tiny dark matter halos form first, with masses maybe 1,000,000 or 100,000,000 times the mass of the Sun. Over time, these halos merge and accrete more material, building up into larger systems, tens of billions, then hundreds of billions of solar masses in dark matter and gas. Ordinary matter, the stuff that can cool and make stars, falls into these potential wells. It radiates away energy, sinks towards the center, and eventually forms the first galaxies. At redshift of about 14, where Mom Z14 and JWST live, simulations based on lambda cold dark matter predicted that you'd mostly see small, patchy galaxies. They'd be faint, with modest stellar masses, sitting in dark matter halos that have not yet grown very large. You'd still be in the regime where feedback from the first stars is relatively brutal. A few supernova can blow a lot of gas out of a shallow potential well. So the expectation was, yes, there will be galaxies, but they should be rare, dim, and chemically primitive. They should look like the first clumps that will later merge into the bigger systems you see at redshift 6 or 7. People quantified those expectations using something called the galaxy luminosity function. Basically, a curve that tells you how many galaxies you get per unit volume at each brightness. Before JWST, we had decent measurements up to redshift about 10 from Hubble and a few ground-based surveys. Beyond that, there were only extrapolations and a handful of disputed candidates. When you take the luminosity function measured at redshift 8 to 10 and extend it to redshift 12 to 15 using lambda cold dark matter models and standard star formation recipes, you get a very steep drop-off at the bright end. Galaxies as luminous as Mom Z14 or JWST should be extraordinarily rare in the observable volume. In many models, you might expect 0 or 1 such object in a whole sky survey, not several in the relatively deep fields JWST has looked at so far. Then JWST came online, and in its first deep programs, it started finding multiple bright galaxies at redshift above 10, and then above 13 with solid spectroscopic confirmation. Instead of one lonely outlier, you had a small but growing population of too bright, too soon objects. When people updated the luminosity function with the new data, the number density of bright galaxies at these redshifts jumped by about an order of magnitude compared to pre-JWST expectations. For every bright early galaxy the old models told you to expect, JWST was showing you something closer to 10.
That's just the raw counts. On top of that, the simulations that produced those expectations weren't lazy. They already included feedback, the same winds, radiation pressure, and supernova explosions we talked about in Mom Z14's starburst. In those models, feedback is particularly effective at early times and in low-mass halos, because the gravitational grip is weaker. When a bunch of massive stars go off in a small halo, they heat and expel gas, slowing down or shutting off further star formation. That keeps most early galaxies small and faint, exactly in line with the hierarchical story. Growth is limited early on, then gradually ramps up as halos merge and deepen. So the pre-JWST simulations had two built-in throttles. First, the growth of dark matter halos themselves, which limits how many massive halos you can have at very early times. Second, the feedback processes, which limit how fast those halos can turn gas into stars. Together, those ingredients gave you a picture where bright, massive, metal-rich galaxies at redshift 14 should exist only as extremely rare edge cases, if at all. You might get one in a big, special, overdense region, but the odds of repeatedly seeing them in different fields would be low. Now put that next to what Mom Z14 is forcing you to accept. You have a galaxy that seems to sit in a relatively massive dark matter halo for its time, is converting gas into stars at a very high rate, has already enriched itself with oxygen and nitrogen, and is doing all of that just 280 million years after the Big Bang. Jade's GS Z1400 is right behind it with similar behavior, and surveys are turning up more bright galaxies at redshift 10 to 13 than you had slots for in the old luminosity function. That's the tension in one sentence. If LCDM plus the standard star formation and feedback physics is perfectly right, galaxies like Mom Z14 should be on the extreme tail of the distribution, almost unseen. But JWST is finding enough of them that you can't hide behind just a weird fluke anymore. Either the dark matter halo population is more favorable to early massive systems than the simplest models predict, or the way gas cools, collapses, forms stars, and responds to feedback at cosmic dawn is very different from the recipes you've been using. Right now, most of the community's effort is going into the second option, tuning the baryon physics. That means exploring scenarios with more efficient gas inflows along filaments, higher star formation efficiency in dense regions, different distributions of stellar masses at early times, and feedback that doesn't blow out as much gas as earlier runs assumed. The goal is to see whether you can rescue the counts and properties of galaxies like Mom Z14 within ЛCDM, without touching the underlying dark matter and cosmological constant picture. But here's the uncomfortable part that keeps the tension high. If you push all those knobs, make star formation more efficient, feedback less destructive, initial stars more massive, you can start to produce Mom Z14-like galaxies in simulations. However, you then have to check that you haven't broken everything else. The galaxy population at lower redshifts, the reionization history, the metal distribution, the stellar mass density over time. Every fix at redshift 14 has consequences at redshift 6, 3, and 0. So the question hanging over the field as more JWST data come in is simple but sharp. Are we just underestimating how extreme normal gas physics can be in the early universe? Or once we've exhausted that, will we still have a residual mismatch that forces us to rethink some part of the ЛCDM story itself? And that leads directly into the next level of the problem, where you stop just saying too bright too soon qualitatively and start quantifying it, counting how many of these things there are, how massive they are, and how much of the early universe's star formation budget they're eating. First, the counts. When people analyze deep fields and build updated luminosity functions at redshift above 10, they keep finding the same pattern. Bright galaxies are more common than you'd expect from Hubble-era extrapolations, by up to roughly an order of magnitude. In simple terms, for every one bright early galaxy the old models told you to expect in a given volume, JWST is seeing something closer to 10. Not all of them are as extreme as Mom Z14, but they live in the same too bright, too soon category. That means Mom Z14 is not a freak lottery ticket. It's sitting on top of a population curve that has shifted upward. Once you accept that, the next step is obvious. You have to look at the total stellar mass these galaxies represent. Mom Z14 and its cousins are each estimated to contain on the order of 10 to the 8th to 10 to the 9th solar masses of stars. Take a few 100 million suns per galaxy as a baseline. If there were only one or two of these in the whole observable volume at that epoch, the total stellar mass they add by 500 million years after the Big Bang would be small, a rounding error in the global budget. But if the number density is 10 times higher than you thought, you suddenly have a lot more stellar mass locked up early on. That pushes against the baseline models in two ways. First, it means star formation efficiency, how much of the available gas gets turned into stars, has to be higher in at least some halos than you assumed. Second, it means feedback cannot be as effective at blowing gas out and shutting things down. Otherwise, you wouldn't build that much mass so quickly. So you're forced to either turn up the efficiency knobs, turn down the feedback knobs, or both, and then hope you don't ruin the agreement with later time galaxy populations. Underneath all of this is the dark matter side, the halo mass function. This function tells you how many halos of a given mass you should have at each redshift in ЛCDM. Bright galaxies like Mom Z14 are usually tied to relatively massive halos, because you need deep potential wells to pull in and retain enough gas. If JWST is telling you there are more bright galaxies at redshift 10 to 14 than expected, it either means there are more massive halos than your ЛCDM calculations say there should be, or that galaxies in the existing halos are much more efficient than you thought. If it's the first case, more massive halos than predicted, that's a direct hit on how dark matter clumps over time. The shapes of the microwave background power spectrum and large-scale structure already constrain that pretty tightly, so you don't have a lot of room to radically change it. That's why most researchers are trying hard to explain the extra brightness with baryon physics first, because touching the halo mass function risks breaking a lot of other data. Then there's the global, how fast is the universe forming stars question, the cosmic star formation rate density. That's just the total mass of new stars formed per unit volume per unit time as a function of redshift. Before JWST, the common picture was that the star formation rate density rises from very early times up to a peak around redshift 2, then declines toward today. At very high redshift, beyond 10, most curves showed a steep drop-off, basically saying there isn't enough time or enough big halos to sustain very high star formation rates. Mom Z14 and the rest of the bright early galaxies push that curve up at the high redshift end. They add a lot of star formation in the first few 100 million years. That can flatten the expected decline, or in some fits even hint at a plateau instead of a sharp fall. If that holds up with larger samples, it matters for several connected problems: how early reionization completes, how quickly the first black holes grow, how many metals are produced and mixed into the intergalactic medium, and how much gas is left over for later galaxy growth. In other words, boosting the early star formation rate density doesn't just make the first few 100 million years brighter, it changes the initial conditions for everything that comes after. So at this point, you might ask a reasonable question. Are we sure we're not simply overestimating everything? Maybe the stellar masses are too high because we assumed the wrong mix of stellar types. Maybe the star formation rates are too high because we mistranslated UV light into mass. Maybe dust is in some weird early configuration and can tweak the spectrum. And strong nebular emission lines sitting in broad filters can boost the apparent brightness at some wavelengths, which, if not modeled correctly, can bias the mass and age estimates. But as JWST keeps collecting higher quality spectra with NIRSpec and longer wavelength data with MIRI, and as ALMA adds independent measurements of gas and dust, the room to hide behind those systematics is shrinking. Better spectra mean you can isolate emission lines more clearly, constrain ages and metallicities better, and separate starlight from nebular contributions. Multi-wavelength data let you see dust directly instead of guessing. Every time a new, cleaner dataset comes in for galaxies like Mom Z14 and Jade's GS Z14, the basic story stays the same. They're bright, compact, and more chemically evolved than the simplest models allowed this early. The exact numbers may move by factors of 2, but they don't drop by an order of magnitude and make the problem vanish. So, zoom out. You have more bright galaxies than expected, each with a lot of stellar mass, implying more or more massive dark matter halos, and a higher early star formation rate density than your pre-JWST curves allowed. You can tweak star formation efficiency, feedback, and stellar populations to ease the tension, but you can't make the whole thing go away without pushing those knobs pretty hard.
Which sets up the next big question for the rest of the story. Do we solve this by accepting that early galaxy formation is just far more aggressive and bursty than we thought, still inside ЛCDM, or do we eventually run out of room and have to consider that something about dark matter, dark energy, or gravity at early times might really be different from the standard model? How far do you push normal astrophysics before you seriously start talking about changing the basic rules of the universe? And where does Mom Z14 actually sit on that line right now? Start with the boring but important point. You do not throw out ЛCDM just because a handful of early galaxies look awkward.
LCDM isn't some random toy model. It's the framework that gets the detailed structure of the cosmic microwave background right, that matches the way galaxies cluster on hundreds of millions of light years, that reproduces baryon acoustic oscillations, lensing statistics, Big Bang nucleosynthesis, all of it. You don't junk a model that passes that many independent tests because a few data points at extreme redshift are hard to fit. If anything, those data points are an opportunity to stress test the model, to see whether you can keep it while upgrading the astrophysics layer that sits on top of it. So the first move is not new physics, it's better astrophysics. One big lever people are pulling is the initial mass function, the IMF. Basically, the recipe that tells you how many stars you get of each mass when a cloud collapses. In the local universe, the IMF is skewed toward low-mass stars, with fewer massive ones. At cosmic dawn, though, it might have been different. If the IMF was top-heavy, meaning you formed proportionately more massive stars per unit mass of gas, that changes the game in a few useful ways. Massive stars are incredibly bright for their mass, especially in ultraviolet. So a top-heavy IMF means a galaxy looks more luminous without needing as much total stellar mass, and that alone can ease the tension with the stellar mass budget we talked about earlier. Massive stars also live fast and die young, so they pump out heavy elements like oxygen and they drive strong winds and explosions on short timescales. That accelerates chemical enrichment and can explain why Mom Z14 and JWST look chemically advanced so early. On top of that, a top-heavy IMF boosts the ionizing photon output, helping with reionization. The cost is that you then have to propagate that assumption through the rest of cosmic history. If you make the IMF top-heavy too long, you overproduce metals, you change the color and brightness of galaxies at later times, and you mess with things like the supernova rate. So the trick is to see if you can have a short-lived, very top-heavy phase at high redshift, say in the first few 100 million years, and then smoothly transition to the more normal IMF you infer locally. That's the kind of detailed modeling people are doing right now. What if the first generation or two of stars was biased toward high mass? Would that be enough to make Mom Z14-like galaxies look less extreme? Another big lever is time behavior, how steady or bursty star formation is. When you see a galaxy like Mom Z14 with very high UV luminosity, you're taking a snapshot. You don't know if that level of activity has been going on for hundreds of millions of years, or if you've caught it during a short, intense burst. Simulations that include strong feedback often produce bursty galaxies at early times. Gas falls in, star formation goes crazy, supernovae and radiation blow out or heat the galaxy dims, then gas cools and falls back in, and the process repeats. If Mom Z14 is in one of those peak phases, it can appear much brighter than its long-term average power. That means the true time-average star formation rate and the integrated stellar mass might be more modest than the snapshot suggests. In other words, you might be seeing the galaxy during the fireworks finale, not during the quieter parts of the show. That can soften the tension with the global stellar mass budget and the halo mass function, because only some fraction of galaxies are in that high luminosity phase at any given time. To capture that properly, simulations need fine time resolution and realistic feedback, not just smooth, averaged-out star formation prescriptions. Combine a top-heavy IMF and bursty star formation, and you get a powerful way to make galaxies look very bright and chemically mature without needing absurd total masses or permanently insane star formation rates. You trade new physics for more extreme but still plausible gas and star behavior inside the existing LCDM universe. That's the direction a lot of current work is going. Push the astrophysics harder, add more detailed radiative transfer, more realistic treatment of clumpy gas, and see if the tension goes away. But, of course, there's a line. If after you've tried top-heavy IMFs, bursty histories, better feedback models, cold gas inflows along filaments, all of it, you still can't match the Townsend properties of galaxies like Mom Z14, then you have to at least look over the fence at the new physics yard. That's where ideas about exotic dark matter and modified gravity come in. One class of ideas is to change the properties of dark matter. Instead of perfectly cold, collisionless dark matter, you can imagine warm dark matter that has a bit more thermal motion, or self-interacting dark matter where particles can scatter off each other.
These changes affect how quickly and on what scales dark matter clumps. In principle, some variants could help you grow massive halos earlier or change the mapping between halo mass and galaxy properties in a way that makes bright early galaxies more natural. But these models are already heavily constrained by other observations, like the structure of small galaxies nearby and the Lyman alpha forest at intermediate redshifts. You don't have a lot of freedom to tweak them without breaking something else. Another route is to adjust the cosmic expansion or gravity itself. People have proposed early dark energy components that briefly change the expansion rate at high redshift, or modified gravity theories that alter how structure grows. Again, these are tightly tested by the cosmic microwave background and by large-scale structure surveys. Any change big enough to drastically alter the high redshift halo population has to thread a very narrow needle to avoid wrecking the excellent fits elsewhere. Right now, Mom Z14 and her cousins are not enough on their own to demand that kind of radical surgery. They apply pressure, but they don't slam the door on ЛCDM. So the honest answer today is a bit boring but important. The safest statement is that our models of early galaxy formation inside ЛCDM were too conservative. We assumed star formation was less efficient, feedback was more destructive, and stellar populations were more normal at cosmic dawn than the new data support. Mom Z14 is one of the galaxies forcing that realization. It's telling simulators you need to let gas flow in faster, let stars form more intensely and more unevenly, and you need to track radiation, metals, and feedback in more detail if you want to match what the sky is showing you. Over the next few years, as more JWST and ALMA data come in, and as simulations get upgraded, either the new, more aggressive astrophysics models will succeed in reproducing the number, brightness, and chemistry of Mom Z14 while still matching all the other constraints, in which case ЛCDM passes another brutal test. Or we'll find that no matter how we push the stellar and gas physics, there is still a systematic mismatch that points to something deeper. Only then does new physics move from clickbait headline to serious mainstream conversation. And that sets up the next step in this story. If you're already testing the limits of normal stars and feedback, what about the more speculative ideas that try to explain these bright early objects with completely different power sources? Things like dark matter-powered dark stars, or very early black holes that light up their host galaxies long before normal star formation would be enough. How far do those wild ideas really get you when you put them next to data from Mom Z14 and its cousins? How far do you go with exotic ideas before they stop helping and start just adding confusion on top of a problem you haven't finished understanding yet? Galaxies like Mom Z14 sit right on that line because they're extreme enough that people are pulling out some very wild proposals, but the data is already cutting a lot of those back down. One of the most talked about ideas is the dark star proposal. A dark star is not dark in the sense of being invisible. It's an object that shines, but not because of normal nuclear fusion in its core. Instead, it would be powered by dark matter annihilation. The concept is this. In the very early universe, before normal stars really got going, dark matter could have been dense enough in some regions that when it clumped with gas, the annihilation of dark matter particles in the core of that clump dumped energy into the gas, puffing it up and making it shine. You'd get a huge, relatively cool, very puffy star-like object made mostly of hydrogen and helium, glowing for a long time without needing to ignite normal fusion in the usual way. Some JWST spectra of very high redshift galaxies, including Jade's Z1401, show features that a few papers have argued could be consistent with one or more dark stars dominating the light. They point to unusual shapes in the continuum or specific absorption features, for example in helium, that don't match basic template spectra of normal young stellar populations as cleanly as you might like. So the idea is maybe part of the flux is coming from one gigantic dark matter-powered object rather than a standard mix of stars. In principle, that would let you get a lot of light without needing to have already built up a huge mass in normal stars. But this is where the oxygen detection from ALMA starts to push back. Remember, a genuine dark star in the original sense is built out of pristine gas, hydrogen and helium left over from the Big Bang, with essentially no heavy elements.
If a galaxy's light were dominated by such an object, and if the surrounding gas were also mostly pristine, you wouldn't expect to see strong signals of metals like oxygen on galactic scales. Yet, in JADE's GS-Z14-0, ALMA clearly sees the 0388 micron line, which means there is already a solid amount of oxygen in the gas. That oxygen can only come from normal massive stars living, fusing elements and exploding as core collapse supernovae. So the moment you see significant oxygen, you know massive, regular stars have already done a lot of work. You can still try to add a dark star on top as an extra light source, but you can't explain the whole system with dark stars alone. A pure dark star galaxy made of untouched primordial gas just doesn't fit the data. That doesn't completely kill the dark star concept, but it pushes it into a narrower corner. Maybe one or a few dark stars coexist with a more normal star-forming population, rather than replacing it. And the more oxygen and nitrogen you see, the less room there is for a "this is all dark stars" story. Another wildcard that gets a lot of attention is early black holes. If Mom Z14 hosts a central black hole that's actively accreting gas, then a chunk of its light could be coming from the accretion disk, not just from stars. That's basically a baby quasar. Accretion onto a black hole is extremely efficient at turning mass into energy, far more efficient than nuclear fusion in stars. So a relatively modest black hole, compared to the galaxy's total mass, can significantly boost the luminosity. If that's happening, it changes the interpretation. Some of the brightness you attribute to stars, and therefore to stellar mass, might actually be powered by a compact accretion disk. That would mean the total stellar mass in Mom Z14 could be lower than current rough estimates, which are mainly based on assuming starlight dominates. It would also naturally give you very energetic feedback, jets, winds, high energy radiation that can help stir up, heat, and chemically process the gas quickly, maybe contributing to the rapid enrichment you see. Do we have direct proof of an active black hole in Mom Z14 yet? Not really. JWST can look for signs like very broad emission lines or specific line ratios that hint at an active galactic nucleus rather than pure star formation. But at these distances and signal levels, it's hard. X-ray observations would be a strong clue, but current X-ray telescopes are not sensitive enough to easily pick up such faint, high redshift sources. So right now, Mom Z14 hosts an active black hole is a plausible scenario, not a confirmed fact. It's on the table because it helps explain high luminosity and intense feedback, but it's not required by the data yet. The next logical question is, if you need an active black hole at redshift 14, where did that black hole come from? We already know that by redshift 7, only about 700 million years after the Big Bang, there are quasars powered by black holes with masses around 1 billion suns. Growing a black hole from a normal stellar mass, say 10 suns, up to 1 billion suns in only a few 100 million years is tough if you stick to standard, slow accretion. That's why people have proposed direct collapse black holes as seeds. In that picture, instead of forming a normal star first, you take a huge gas cloud, maybe 100,000 to 1 million solar masses, and under the right conditions, it collapses straight into a massive black hole without fragmenting into many smaller stars. That gives you a head start, a seed black hole of around 100,000 solar masses instead of 10. From there, it's much easier to grow to 1 billion solar masses by redshift 7. Galaxies like Mom Z14 are exactly the kind of places you'd look for such seeds. They're dense, gas-rich, and forming stars like crazy. The same conditions that make starburst activity possible, high inflow rates, strong gravitational potentials, lots of gas piling up in the center, could also favor direct collapse in some regions, if the gas avoids fragmenting. So in one line of thinking, Mom Z14 type systems aren't just strange early galaxies. They're the birthplaces of the black hole seeds that will later power the most extreme quasars we see at slightly later times. For you watching this, the takeaway is not that you have to believe in dark stars or commit to a specific black hole seed model right now. The key point is that galaxies like Mom Z14 have moved these ideas out of the speculative corner and into the zone where they have to confront real data. Dark stars used to be a fun theoretical construct. Now, people are actually checking JWST spectra and asking, does this feature really demand something like that, or can normal stars explain it? Direct collapse black holes used to live mostly in simulations. Now, observers are hunting their signatures in systems like Mom Z14. The presence of these extreme galaxies at redshift 14 means the early universe is no longer a blank canvas where you can hide anything. It's a measured space with real spectra, real lines, real luminosity functions. Any exotic idea, dark stars, early black holes, modified dark matter, has to pass that test. It has to explain Mom Z14 and Jade Z14-0 and the whole population of bright early galaxies at redshift 14, not just one feature in one object. And even if you end up solving most of the puzzle with just aggressive star formation and feedback, these wild ideas still matter because they remind you how much parameter space there is at high redshift. The early universe can host objects and processes that simply don't have close analogs today. That's exactly why galaxies like Mom Z14 are so valuable, because they force the field to map out that space using actual observations, not just thought experiments. Now, if you accept that Mom Z14 may be home to extreme stars, maybe even an early black hole, and is blasting out enormous amounts of high-energy light, the next obvious issue is what all that radiation is doing to the universe around it. How much is a galaxy like Mom Z14 really contributing to ending the cosmic dark ages and reionizing the hydrogen fog between galaxies? And what happens if there are far more of these cosmic blowtorches than we expected? How much damage can one tiny galaxy actually do to the hydrogen fog of the early universe? And does Mom Z14 move the needle on when the cosmic dark ages really ended? Start with the raw output. Every massive hot star in Mom Z14 is a factory for ionizing photons, the kind of ultraviolet light energized enough to knock electrons off of hydrogen atoms. When you have a star forming rate of several to a few tens of solar masses per year, like the estimates for Mom Z14, that translates to something like 10 to the 53 to 10 to the 54 ionizing photons every second. That's a 1 with 53 or 54 zeros after it. Every second, coming out of a star-forming region only a few hundred light-years across. Those photons don't just sit there, they stream out into the surrounding gas. Close to the galaxy, the density is high, so many photons get absorbed quickly, carving out an ionized region around the star-forming core. That's a bubble where hydrogen is mostly ionized instead of neutral. Farther out, the gas is thinner, and the bubble can grow larger before the photons are used up. For a galaxy as intense as Mom Z14, you expect that ionized bubble to reach tens of kiloparsecs in radius, tens of thousands of light years in the intergalactic environment around it, depending on how long the starburst lasts and how clumpy the gas is. So even though the galaxy itself is only a few hundred light years wide, it can dominate the state of hydrogen over a much larger region. Inside that bubble, the gas is hotter, more transparent, and more favorable for later galaxy formation. Outside the bubble, the universe is still mostly neutral, still in the tail end of the dark ages. In that sense, Mom Z14 is not just a passenger in the early universe, it's an active agent reshaping its local environment. Now, zoom out. Reionization, the process of turning most of the hydrogen in the universe from neutral back into ionized, requires an enormous amount of ionizing photons. You need enough photons to ionize every hydrogen atom at least once, and in practice more than that, because recombination keeps happening. The question has always been, who supplied that photon budget? The usual answer is lots of faint galaxies at redshift 6 to 10, each contributing a bit over long periods. Theoretical models and Hubble data suggested that if you integrate over all those galaxies, including many too faint to see directly, you can just about hit the needed ionizing photon count by around a billion years after the Big Bang. Mom Z14 and similar galaxies push on that picture in a straightforward way. If there are more bright, compact, high redshift galaxies than we thought, each dumping out around 10 to the 53 to 10 to the 54 ionizing photons per second, then the contribution from the bright end of the population goes up. That can move the timing and the shape of the reionization history.
Instead of a slow, faint drizzle of photons from mostly tiny galaxies, you have additional strong sources turning on earlier, carving out larger bubbles sooner. If this is common, not rare, reionization might start earlier and proceed faster in some regions than pre-JWST models assumed. This feeds back into how we interpret other datasets. The cosmic microwave background carries subtle imprints of when free electrons were present in the universe through a parameter called the optical depth. Quasar spectra at redshift 6 to 7 show how much neutral hydrogen was left along each line of sight through Lyman alpha absorption. Both of these provide constraints on when reionization was mostly complete. If galaxies like Mom Z14 are common enough, you may need to adjust the assumed contribution from bright sources in the models that connect those constraints. That doesn't mean the basic story, galaxies reionize the universe, is wrong, but it changes which galaxies are doing the heavy lifting and when. There's a major caveat though, and it's one of the biggest unknowns in the whole problem: the escape fraction. That's the fraction of ionizing photons that actually make it out of the galaxy into intergalactic space instead of being absorbed by gas and dust locally. If most photons are absorbed in the galaxy's own interstellar medium, they help carve out a small bubble close in, but don't contribute much to reionizing the wider universe. If a significant fraction escape through holes and channels in the gas, they can travel far and ionize hydrogen on much larger scales. For a compact galaxy like Mom Z14, the escape fraction is not obvious. On one hand, high gas densities and possibly significant dust can trap photons. On the other hand, strong feedback from supernovae and stellar winds can blow cavities and channels in the gas, like chimneys, letting some fraction of photons stream out relatively unimpeded. The geometry can be messy. Along some directions, the escape fraction might be high. Along others, almost zero. Right now, escape fraction at these redshifts is basically inferred from models and indirect indicators, not measured directly. But Mom Z14 offers a chance to tighten that up. Because it's so bright and so compact, and because JWST can get decent spectra even at this distance, it's a good test case for linking observed line strengths, continuum slopes, and possibly future radio or millimeter observations to realistic 3D models of gas and dust. If you can pin down the escape fraction in a system like this, you can better estimate how much it actually contributes to the global photon budget, rather than just its local bubble. In the end, reionization is a cosmic energy budget problem. You're trying to close a spreadsheet with a few key columns: how many galaxies, how bright, how long they stay active, and what fraction of their ionizing photons escape into intergalactic space. Before JWST, that spreadsheet was dominated by faint galaxies around redshift 6 to 10, with relatively modest contributions from brighter systems. Mom Z14 adds a big unexpected line item in the very early, very bright, very compact category. If there are many more entries like it, you can't ignore them. You have to update the whole budget. And once you start rewriting that spreadsheet, another question becomes crucial. To place Mom Z14 correctly in the universe's history and in reionization models, you need to know its distance and redshift precisely. So how do you go from "this is a red dot in a deep image" to "we know it's sitting at redshift 14.44 and its light has been traveling for about 13.5 billion years"? The first step is almost always a rough guess, a photometric redshift. JWST's NIR cam takes very deep images through multiple filters, each one capturing a slice of infrared wavelengths. For a normal galaxy at moderate distance, you see a smooth change in brightness across those filters. For an extreme high redshift galaxy, something different happens. Because neutral hydrogen absorbs light below a certain ultraviolet wavelength, you get a sharp drop in the galaxy's flux at what's called the Lyman break. As the universe expands and stretches the light, that break slides from the ultraviolet into the infrared. For a galaxy like Mom Z14, that break lands between two of NIR cam's redder filters. In the bluer filters, you see almost nothing at that position, just background noise. In the redder filters, the galaxy suddenly appears.
You compare that pattern, dark here, bright there, to model spectra of galaxies at different redshifts, and you ask, at what redshift does the Lyman break land between these exact filters? That gives you a photometric redshift, a first estimate based purely on colors. It's like matching a fingerprint when you only have a few clear ridges, not the whole pattern. It's good enough to say, this is probably at redshift around 14, but not good enough to rebuild cosmology on its own. To really trust the distance, you need a spectroscopic redshift, the locked-in answer. That's where JWST's NIR SPECT instrument comes in. Instead of just measuring brightness in broad filters, NIR SPECT spreads the light out by wavelength, producing a spectrum. In that spectrum, you're looking for two main things. First, the position of the Lyman break, where the flux drops sharply at shorter wavelength because hydrogen absorbs the photons. Second, a set of emission or absorption lines from elements like hydrogen, oxygen, and nitrogen, each at very specific rest frame wavelengths. For Mom Z14 and for JADE's GS-Z14-0, spectra show a clear cutoff in the continuum where you expect the Lyman break to be if the redshift is around 14. On top of that, they reveal several lines shifted into the near-infrared at positions that match known ultraviolet lines multiplied by the same factor. When you measure exactly where those lines sit and compare to their rest frame values, you get a precise redshift. The uncertainty is small. For these galaxies, the error in Z is on the order of a few hundredths, so the difference between, say, 14.44 and 14.40. That might sound like a tiny detail, but in cosmic time, even a change of 0.1 in redshift at this epoch corresponds to tens of millions of years difference in age. So when we say Mom Z14's redshift is pinned down to within about a tenth, we're saying its light left when the universe was about 280 million years old, plus or minus a few tens of millions. When you're dealing with a total age of 13.8 billion years, that's extremely good timing for such a distant target. There's another independent way to check these distances, and that's where ALMA comes in. ALMA observes at millimeter wavelengths from the ground. It's sensitive to cold or warm gas emission like the I3 line at 88 micrometers in the rest frame. When that line is redshifted by about a factor of 15, it moves into the millimeter range ALMA can see, around a millimeter, which is a million nanometers. For JADE's GS-Z14-0, ALMA detects that oxygen line at exactly the wavelength predicted for a redshift of about 14.2. That's huge because it's a completely different instrument, in a different wavelength regime, with different systematics giving you the same answer as JWST. If JWST says this galaxy is at redshift 14.2 based on ultraviolet and optical rest frame signatures, and ALMA says this gas line is at a wavelength that only makes sense at redshift 14.2, you can be very confident that distance is real. For Mom Z14, similar multi-instrument strategies are either already underway or being planned, because that cross-check is what turns an impressive claim into a robust measurement. Given all of that, how seriously should you take the possibility that Mom Z14 is actually some weird nearby object pretending to be an ultra-distant galaxy? This used to be a real problem in the pre-JWST era. Brown dwarfs in our own galaxy or dusty galaxies at moderate redshifts can sometimes produce colors that mimic a Lyman break in broad filters. Without spectra, those imposters could sneak into high redshift samples. In Mom Z14's case, that scenario is very unlikely. The full spectrum, including the shape of the continuum and the positions of multiple lines, matches what you expect for a young, star-forming galaxy at very high redshift, not for a cool star nearby or a dusty galaxy at Z2 or 3. Cool brown dwarfs have characteristic molecular absorption features that don't show up here. Dusty galaxies tend to have strong signatures in the mid-infrared and submillimeter that don't align with what we see for Mom Z14. On top of that, the existence of several galaxies with very similar spectral patterns and photometric behavior at very similar redshifts makes the "we keep getting fooled by bizarre local objects" explanation statistically weak. It's much more straightforward to say this is a genuine population of high redshift galaxies, and Mom Z14 sits at the extreme end of that population. And even with all the technical detail, the distances involved here are so large they crush intuition. A single light year is about 9.46 trillion kilometers, or about 5.88 trillion miles.
Mom Z14's light has been traveling for roughly 13.5 billion years. Even if you just multiply 1 light year by 13.5 billion, you're already beyond what your brain can really picture. Then remember that because the universe expanded while that light was in flight, the current proper distance is closer to 34 billion light years. You're stacking billions of light years, each of which is already trillions of kilometers. No combination of metric and imperial units truly makes that feel normal. You can say 40 trillion years on a commercial jet or millions of times the Milky Way's diameter, but at some point, the numbers just tell you one thing. This galaxy is very close to the edge of what we can ever hope to see. Mom Z14 forces you to accept that we are now doing precision measurements at the extreme limits of observable space and time. And those measurements are solid enough that we're willing to question the way we thought the early universe built its first structures. And once you accept that the distance is real and the tension with theory is not just a calibration error, the next obvious question is, can our state-of-the-art simulations actually catch up with what JWST is showing us? Or are observers and theorists now in a race where the sky keeps staying one step ahead of the computers? How close are the best simulations on Earth to actually recreating a galaxy like Mom Z14, instead of just being surprised by it on a JWST image? Right now, you've basically got two worlds trying to meet in the middle. On one side, there are massive simulation projects like Illustrious TNG, Renaissance, and a whole new wave of JWST-era runs. They evolve billions of particles of dark matter and gas step by step, following gravity, gas cooling, star formation, and feedback over billions of years. They run on supercomputers that would crush an entire country's worth of normal laptops. On the other side, you've got real data. Near-cam images, near-spec spectra, ALMA lines, and objects like Mom Z14 and Jade's GS Z14-0 that don't care what your code predicted, they just exist. In the earlier generation of simulations, before JWST, the focus was mostly on matching what we saw at redshift 6 and below. So the knobs, star formation efficiency, feedback strength, how easily gas can cool, how radiation escapes, were tuned to get the right number of Milky Way-like galaxies, the right clustering, the right stellar mass density at later times. High redshift galaxies above redshift 10 were more like a side prediction, not a primary target. When JWST started dropping confirmed galaxies at redshift 13 and 14 that were this bright and this enriched, the first reaction in the simulation community was basically, okay, our early time output is off, how much can we fix without wrecking everything else? That's where the retuning starts. Simulators are now running dedicated JWST-focused boxes, smaller regions with very fine resolution, pushed to earlier times, and with more aggressive physics. They're turning up star formation efficiencies in dense early halos, so more of the gas gets converted into stars quickly. They're experimenting with less catastrophic feedback in tiny halos, so starbursts don't instantly shut themselves down. They're testing top-heavy initial mass functions in the earliest phases to boost UV light and metal production without needing absurd total stellar masses. Every run is basically the same question. If I let early galaxies behave more violently and more efficiently by redshift 14 and still match the galaxy population at redshift 6, 2, and 0, the main metric they're trying to hit is the luminosity function at high redshift, how many galaxies you have at each brightness between, say, redshift 10 and 15. Observers take JWST deep fields, count galaxies, measure their brightness and redshifts, and build that curve from data. Simulators take their synthetic universes, run mock observations, and build the same curve from their virtual galaxies. If the curves line up, you call it a success. If the simulated bright end still sits way below the JWST bright end, you know you're not done. Early work is showing that you can get closer by letting gas flow into early halos more efficiently, and by not blowing everything out with feedback the moment a starburst starts.
If gas streams in along cosmic filaments and keeps refueling small halos, and if supernova and stellar winds stir up the gas without ejecting all of it, then you can maintain high star formation rates for longer. That naturally produces more bright galaxies earlier. Add in a slightly top-heavy IMF, and the same stellar mass gives you more UV light and faster enrichment. Suddenly, Mom Z14 goes from impossible to rare but not insane in some of these new runs. But there's a catch, and it's important. Every time you tweak these knobs to make the early universe more active, you risk overshooting at later times. If you convert gas into stars too aggressively at high redshift, you might end up with too many massive galaxies too early, or with a too high stellar mass density by redshift 2 or 3. If feedback is too gentle in small halos, you might fail to reproduce the observed number of faint dwarfs at lower redshift. So the simulations have to walk a tightrope. Extreme enough at Z times 14 to match Mom Z14, but restrained enough later on to still match everything else we've already measured. On top of that, you can't forget the selection effects in the observations. JWST is incredibly sensitive, but it doesn't see the whole sky. Deep fields are tiny pencil beam cones, maybe a few dozen square arc minutes, piercing the universe along very narrow lines. That means cosmic variance, random differences in how dense or underdense a particular line of sight happens to be, can skew your counts. If a deep field happens to hit a rare overdense region, you'll see more bright galaxies than average. If it hits an underdense patch, you'll see fewer. Observers and theorists know this, so when they compare luminosity functions, they're now explicitly folding cosmic variance into the error bars. That's why you don't see serious people claiming Lambda CDM is dead based purely on the first few JWST fields. Instead, you see language like tension, mismatch, or overabundance compared to baseline models, with the caveat that wider surveys are needed to nail down the average. As more fields at different positions on the sky come in, that cosmic variance uncertainty will shrink, and the counts will either stay high, making the problem real and robust, or drift back toward the conservative predictions. So the race you're watching right now is pretty direct. JWST pushes a little deeper, a little wider, and drops a new Mom Z14 class galaxy or a new batch of bright objects at redshift 12 and 15. The simulation teams then go back to their codes, rerun early universe boxes with updated physics, and see if those galaxies appear naturally in their virtual universes. If they do, and the same model still matches all the lower redshift data, that's a big win for better astrophysics inside Lambda CDM. If they don't, and the gap between simulations and observations refuses to close even after reasonable tuning, then the pressure builds to look at more radical options. Right now, you're watching JWST do exactly what it was built to do. Be the pathfinder. It's the discovery machine. It goes insanely deep on small patches of sky, pulls out objects like Mom Z14, and then gives you the spectra you need to measure their distances and chemistry. It's showing you that these galaxies exist, and roughly what they're like on the inside. But there's a limit built into the hardware. JWST's field of view is small. Each deep field is a tiny cone through the universe, a narrow pencil beam. Great for details, not great for statistics. It's like having the best microscope in the world and only being able to look at a few spots on the slide. That's where the next wave of telescopes come in, starting with NASA's Nancy Grace Roman Space Telescope. Roman is designed to do in the infrared what Hubble did in visible light, but with a field of view hundreds of times larger than Hubble's. It won't go as deep as JWST in a single pointing, but it will cover huge chunks of sky. For this story, that matters a lot more than one extra ultra-deep image. Roman will find large samples of high redshift galaxies, including bright ones like Mom Z14 and Jade's GS-Z14-0, over wide areas. That's how you move from "we found a few extreme objects in a small patch" to "we know how common these things are across the universe." If Roman surveys show that Mom Z14 class galaxies are extremely rare, even in wide fields, then you're looking at a genuine tail event, a statistical freak that just happens to be spectacular. If Roman instead finds that galaxies almost as bright and as early as Mom Z14 pop up regularly once you look over enough area, then the whole luminosity function at high redshift really does sit higher than the old models. Roman is the tool that will tell you whether Mom Z14 is a curiosity or a sign that the early universe is systematically more active than you thought. At the same time, giant ground-based telescopes are coming online to attack the problem from the other side: resolution and dynamics. Telescopes like the Extremely Large Telescope, ELT, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, will have primary mirrors in the 25 to 40 meter class, far bigger than JWST's 6.5 meters. With adaptive optics correcting for the atmosphere, they'll be able to sharpen their images to approach JWST's angular resolution, but with different instruments and more flexible observing schedules. For early galaxies, that means you can go beyond "this is a small blob" and start asking, does this thing rotate like a disk, or is it a merger of several clumps? Are there velocity gradients that tell you gas is streaming in along one axis and blown out along another? Do you see multiple components with different line widths, hinting at subclusters or ongoing mergers? Ground-based giants can map the motions of gas and stars in Mom Z14 type systems, using spectral lines shifted into the near-infrared and turn them from static pictures into live three-dimensional objects with measured kinematics. Combined with JWST's chemistry and continuum spectra and ALMA's view of cold gas, you start to build a real 3D assembly history, not just a single snapshot. Then you have the longer wavelength facilities, the ones that pick up where JWST drops off. JWST is powerful in the near and mid-infrared, but it can't see the coldest gas and dust directly at high redshift. Future far-infrared and radio observatories will target exactly that regime. They'll trace molecular gas, the fuel for future star formation, through lines like carbon monoxide and C2, and they'll map dust emission that tells you where the densest, coldest regions are hiding. Combined with ALMA and other arrays, you'll be able to say, this much gas is still available, this is how it's distributed, these are the densest clumps, and this is where the next generation of stars will form. That shift is important. Right now, for many of these galaxies, you mostly see bright blob in the UV and optical rest frame with some metal lines. With a full suite of future instruments, you move to, we know the gas reservoir size and solar masses, we know which parts are metal-rich and which are metal-poor, we know where the star-forming clumps are, and we know how the whole thing is moving. Instead of just proving that galaxies like Mom Z14 exist early, you'll be able to write down detailed formation scenarios backed by direct measurements. How fast gas flows in, how quickly it turns into stars, how bursty and extreme those first star-forming events can be, whether a central black hole is involved. So why should you care about this instrument zoo? Beyond the obvious, more telescopes are cool. Because without them, you're stuck in a dangerous zone. Strong hints, small samples, big claims. JWST on its own can show you a handful of extreme systems and tell you something is off with our pre-JWST expectations. That's already happening. But to say with confidence that the early universe is really too bright, too fast, in a way that truly forces changes to models, you need large samples across many lines of sight, with solid cross-checks from independent instruments. Roman gives you the large samples and the wide field statistics. The ELT, TMT, and GMT give you the detailed dynamics and structure. Future far-infrared and radio facilities give you the cold gas and dust. Together with JWST and ALMA, you turn Mom Z14 from a single spectacular data point into just one member of a well-characterized population. At that point, you can stop arguing over whether this or that galaxy is an outlier and start fitting full distributions. How many galaxies at redshift 14 have high metallicity? How many are compact? How many host black holes? How their properties correlate with halo mass? That's when the tension with LCDM or with your galaxy formation recipes becomes a precise testable diagnostic instead of a vague, "this feels wrong." With enough data, you'll know whether the fix is as simple as "we underestimated early star formation efficiency," or whether the whole high redshift universe really is telling you that some piece of the standard picture needs to be rewritten. And that brings you to the real point of all this. Mom Z14 is not just an impressive record or a pretty JWST image. It's a test case for how you react when reality and simulation diverge. So, to wrap this all together, you need to ask one final, uncomfortable question. When you put distance, brightness, chemistry, number counts, and future surveys all on the same table, what does Mom Z14 actually mean for your picture of the universe, and how far are you really from having to change that picture in a serious way? So what does Mom Z14 actually do to your picture of the universe once you strip away the hype and just look at where this thing sits compared to what we expected? On paper, Mom Z14 is just one galaxy, one data point. It's not a full survey, it's not a new law of physics, but it lives in a part of parameter space that used to be almost empty in our models. Very high redshift, very bright, very compact, and already chemically evolved. Before JWST, the standard plots basically said, up here at this distance with this brightness and this metallicity, you might get a few objects in the entire observable universe, or maybe none. And then JWST points at a small patch of sky and finds Mom Z14 sitting exactly in that there should be almost nothing zone. That's why it matters. It's not that we had no galaxies at all in our predictions, it's that we didn't expect this kind of galaxy, with this combination of distance, luminosity, size, and chemistry. There are a few ways you can tell the story from here, and they're not mutually exclusive. The first, and currently most likely, is the "we were wrong about the details" story. In this version, LCDM is fine at the global level, but the way we model normal matter, gas, stars, radiation, feedback, at early times is too simple. We underestimated how efficiently gas can flow into early halos, how quickly it can form stars in very dense regions, and how bursty and extreme those first star-forming events can be. In that case, Mom Z14 is the universe telling you your baryon physics needs an upgrade, not your whole cosmology is broken. The second story is more adventurous. We've glimpsed new actors. That's where ideas like top-heavy initial mass functions, rapid black hole seeds, and maybe even dark matter-powered dark stars come in. Here, the basic framework is still LCDM, but the early universe hosts kinds of objects you don't really see today. Star-forming clouds might preferentially make massive stars at cosmic dawn, changing the light output and enrichment speed. Dense, gas-rich regions like Mom Z14 might be the exact birthplaces of direct collapse black holes that later grow into billion solar masters by redshift 7. A few systems might even host exotic configurations where dark matter briefly powers star-like objects. In this story, Mom Z14 is not just a statistical outlier, it's a glimpse into phases of physics and object types that only exist in the first few 100 million years. The third story is the most radical, and right now the least favored. The universe is hinting at deeper changes. That means fundamental physics, tweaks to dark matter, early dark energy, or gravity itself. You only go there if you truly can't fix the tension with any reasonable astrophysics. At that point, you'd say something like, the halo mass function at high redshift is wrong in Lambda CDM. Structure grows faster than it should, or the expansion history at early times is different from what we thought. Most cosmologists are very cautious about this because Lambda CDM is so tightly constrained by the cosmic microwave background and large-scale structure. To overturn that, you need a lot more than Mom Z14 and a few cousins. Right now, people are definitely exploring these ideas, but the main weight of opinion is still on the first two stories, more extreme baryon physics, maybe plus some new early universe actors. There's a bigger lesson in all of this that has nothing to do with the exact value of a redshift or a star formation rate. It's about how cosmology actually behaves when the sky doesn't match the simulation. Mom Z14 is not being treated as a crisis, it's being treated as a stress test. Lambda CDM has already passed several of these: the accelerated expansion, the detailed microwave background structure, baryon acoustic oscillations, lensing measurements. Each time, you push into a new regime, new redshift, new scale, new type of object, and ask, does the same framework still work if we tune the details correctly? Early galaxies are the latest frontier. When JWST drops Mom Z14 on the table, the response isn't throw everything out. It's, all right, turn every dial we have on star formation, feedback, and radiative transfer and see how far we can get before we even think about touching the core cosmology. That's how a mature field handles surprises. You keep the big structure unless it absolutely fails, and you accept that the messy, small-scale physics inside halos is often where your first guesses will be wrong. And then there's you, sitting in the middle of this. You're on a planet about 150 million kilometers from a fairly ordinary star, using a device that can stream data and images built from photons that left the galaxy 34 billion light-years ago in proper distance. That light started its trip long before the sun existed, long before the Milky Way's disk formed, long before there were planets, dinosaurs, or anything like what you'd call a normal galaxy. All the jargon we've used, redshift, metallicity, luminosity function, halo mass, is just a toolkit, a way for humans to compress that absurd gap in time and space into something you can talk about without your brain locking up. The real punchline is simple and a bit unsettling. The universe is more efficient at organizing itself than we thought. Give it less than 300 million years, and in at least some places, it can build dense halos, pull in gas, ignite starbursts, enrich that gas with oxygen and nitrogen, maybe grow black hole seeds, and blast enough radiation into space to carve holes in the cosmic fog. Mom Z14 is proof of that. It's the universe pointing at our pre-JWST models and saying, nice first draft, but you missed a few things. So when you hear Mom Z14 in future papers or videos, don't treat it as just that really far galaxy JWST found. Treat it as a marker of a shift. It's the moment we realized our mental picture of the first few 100 million years was too quiet, too slow, and too simple. And here's the part that should stick with you. The next JWST deep field could easily find something even more extreme, a galaxy at an even higher redshift, or a system that's even more compact and metal-rich, or a clear early black hole that blows past our current growth models. All those will force another round of updates to how we think the cosmos builds itself from almost uniform hydrogen into the complex structure you live in now. The sky is not done surprising you, and Mom Z14 is just one of the first big warnings that the early universe is a lot busier and a lot more capable than the neat diagrams in old textbooks ever suggested. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.